Alright, let's get started. So we have one more lecture and it's on diagonalization, so let's pick up where we left off last time. So what were we talking about? We started talking about diagonalizability. Should we just give let's just do a quick overview of what we did? So we started, first I gave some general fact that if you have eigenvectors for distinct eigenvalues, then those eigenvectors are linearly independent. And that's used in discussing diagonalizability. So one way to define diagonalizable matrices is that those are the square matrices that have the form P times D times P inverse, where D is a diagonal matrix. And we saw that if you can write A in that form, what has to happen is that the columns of P are eigenvectors for the eigenvalues, and the eigenvalues are given along the diagonal. And so the diagonalizable matrices are the ones where you have a basis of eigenvectors, a basis of Rn consisting of eigenvectors of A. Because those are the vectors that will form the columns of the matrix P. And then we looked at an example, and then we saw that there are many different possibilities for P and D, because you can always switch the order that you write the eigenvalues in, as long as you keep the eigenvectors in the corresponding order. And you can also just scale the eigenvectors, right? So there's multiple possibilities for P. I mean, if you have, say, a 3x3 matrix, right, and let's say it has two distinct eigenvalues, 2 and 1. Well, let's just do a quick example. Let's just say that A is the matrix. Okay. A scales the xy plane by a factor of 3 and scales the z-axis by a factor of 4. Let's say A is a matrix that does that. Well, one possibility for A is to just have the diagonal matrix 3, 3, 4. Right? In this case, if you have a diagonal matrix, is A diagonalizable? Yes, it is. It has the form PDP inverse. I mean, A would be equal to your D in this case. And what would be P? P would be equal to the identity, right? We have the identity times D times the identity inverse. That's just going to equal D. So you have the xy, so here's the x-axis, here's the y-axis, here's the z-axis. and then this plane gets stretched by a factor of 3, and then this line gets stretched by a factor of 4. Well, another thing you can do is you can also just take, so your matrix P was formed by taking these three, 1, 0, 0, 0, 1, 0, and 0, 0, 1 as your V1, V2, and V3. Right. But you could also take, maybe you could take this vector and that vector as your V1 and V2. And then you can take, I don't know, how about this vector as your V3? So one possibility for P, so P could be the identity, the 3 by 3 identity matrix, or for instance, or something else, like it could be, so I need the first two vectors to be eigenvectors with eigenvalue 3, and then the third one needs to be an eigenvector with eigenvalue 4 because of the way I wrote 3, 3, and 4. So you could have V1 be, you just need the z component to be 0, and you need two linearly independent. So how about 1, 1 and negative 1, 1? Right, these two vectors form a basis for the xy plane, and then in R3, right, this is in R3, and then your V3 could be 0, 0, 7 or something, right? So A can also be written as 1, negative 1, 1, 1, 0, 0, 0, 0, 7, 3, 3, 4, and then this matrix inverse. This matrix is the same. It turns out that if you multiply these three matrices across, you'll just end up getting this. So the point I'm trying to make is that there's lots of different possibilities for P and D. Okay, P, all you need to make a P is just that the columns are eigenvectors that correspond to, they have to be linearly independent eigenvectors corresponding to the eigenvalues. But that's the only requirement. There isn't like a specific eigenvector you have to use. Okay, anyway, so that was that, and then we wanted to talk about how to tell if a matrix is diagonalizable. Yeah, so here's one example, right? 3, 1, 1, 3. And then we gave an example that wasn't diagonalizable. And we talked about how we want to test for diagonalizability. And we started introducing some terminology we need. So one of the vocab words is the multiplicity. Okay, nope. Uh-oh. The multiplicity of a root. Hopefully you have heard of the term multiplicity in some context, right? And maybe in a pre-calculus class or something. Like if talk about a double root or a triple root. A double root would be a root that has multiplicity 2, and the triple root is a root with multiplicity 3. And we said that the polynomial splits if it has this form, if you can factor it into a bunch of linear factors, right? So these are linear factors, where these constants are real numbers. So technically it should be splits over the real numbers, but that's something I'm sort of sweeping under the rug. Okay. So when can you have a polynomial that is not split? Basically, if you have quadratics with no real roots. So for instance, for this polynomial doesn't split because it has no real roots. If it had two real roots, then you could factor it and then it would split. So it would be like something like this. This has two real roots. This one has no real roots. So it doesn't split. And then this polynomial splits. And then what I wanted to emphasize, how did I do that? What I wanted to emphasize is that they don't have to factor into completely distinct roots, distinct factors. So you could have 3 t plus 4s. And in this case, the multiplicity of -4, so -4 has multiplicity 3, right? But this polynomial still splits. Okay. And are we ready for, we're almost ready for the criterion. We just need one more fact, one more general fact. So let's say that, again, you have an n by n matrix A, and you have an eigenvalue lambda, okay. And let's say, so a bit more of a setup. So if lambda is an eigenvalue of A, right, then lambda is a root of the characteristic polynomial. So that means that you can factor out, let's say that's the characteristic polynomial of t, of A, right? So if P of t is the characteristic polynomial of A, then lambda is a root, so you can write P of t as t minus lambda. You can factor out the t minus lambda, and you can factor out the power of t minus lambda. So let's say E, and then g of t, right? Where g of lambda is not equal to 0. So that means that you can't factor out any more t minus lambdas. Well, so that E is the multiplicity of lambda. Right. Now that's not the theorem. The theorem is that the dimension of the lambda eigenspace right, all the vectors that are scaled by a factor of lambda has to be less than or equal to E. So that's the multiplicity of lambda, and sometimes in the context of eigenvalues, this is called the algebraic multiplicity. So let's use that terminology. And the dimension of the eigenspace, that's sometimes called the geometric multiplicity of lambda. Okay. So the geometric multiplicity is always less than or equal to the algebraic multiplicity. And by the way, what can we always say about the dimension of the eigenspace? Can the dimension of the lambda eigenspace be 0? No, because an eigenspace, by definition, has to have a non-zero vector, right? Eigenvectors are, by definition, non-zero vectors. And so the dimension has to be greater than or equal to 1. This fact that it's greater than or equal to 1, that's not the main content of this theorem that I'm trying to explain. The main content is that the geometric multiplicity is less than or equal to the algebraic multiplicity. Okay. Now I think we're ready for the theorem. So this is the main result of this lesson. Test for diagonalization. So again, you have an n by n matrix. Let A be an n by n matrix. So one is A diagonalizable. A is diagonalizable. So again, we have two ways of thinking about it. It has the form PDP inverse, right? That's one way. The second way is that it has a basis of eigenvectors. And the way that's, a criterion for checking if a matrix is diagonalizable or not is both, okay, the first thing, the characteristic polynomial of A splits into a bunch of linear factors, and for each eigenvalue lambda, okay, of A, the geometric multiplicity has to equal the algebraic multiplicity. So the dimension of the lambda eigenspace has to equal the multiplicity of lambda, so the algebraic. I mean, when I say the multiplicity of lambda, I usually just mean the multiplicity of lambda as a root of the polynomial, of the characteristic polynomial. Okay. Well, I think we better look at an example. Let's do some examples to see if these matrices are diagonalizable. Is this matrix, let's do a 2 by 2 example, 1, 0, 1, 3, diagonalizable. Well, let's first look at condition 1, the characteristic polynomial. Okay, well, the characteristic polynomial is just, I have two distinct so can I see what the eigenvalues are? Yes, this is a lower triangular matrix. I have 0 here. The eigenvalues are 1 and 3. So the characteristic polynomial P of lambda is lambda minus 1 times lambda minus 3. Right. You could also just do it out. I mean, you just take away lambda along the diagonal and multiply them, and you're going to get this. Okay, so this characteristic polynomial split. Now, if you think about it, well, okay, so I have these two eigenvalues. Lambda 1 is 1, lambda 2 is 3. Now, what's the dimension of the lambda eigenspace? Well, if you think about it, can we figure that out without actually finding a basis for the eigenspace? What's the algebraic multiplicity of lambda 1? So the algebraic multiplicity of the eigenvalue 1 is 1 because I have a 1 here. And the algebraic multiplicity of lambda 2 is also 1 because this is lambda minus 3 is to the power of 1. Now, there's a general fact, right, that the geometric multiplicity is less than or equal to the algebraic multiplicity. So in this case, do we know what the geometric multiplicity is? Yes, it's 1, because your multiplicity in this case is just 1. Right? The E in this case is 1, but the geometric multiplicity is always at least 1. So, I mean, the only number that's less than or equal to 1 and is greater than or equal to 1 is 1. So the geometric multiplicity is equal to 1. Okay. For both of these eigenvalues. And therefore, what can you conclude from this diagonalization test? The characteristic polynomial splits, right? Yes. Because I have two linear factors, and then for each eigenvalue, the dimension of the lambda eigenspace, the geometric multiplicity, is equal to the algebraic multiplicity because they're both 1. So the second condition is also true. Therefore, A is diagonalizable. Okay. Great. And if you think about what happens in general, if you have a 2x2 matrix, we can actually figure out the whole story behind diagonalizing 2x2 matrices. Because a 2x2 matrix, it could either have 0 eigenvalues, right? If it has no eigenvalues, no real eigenvalues, it's not diagonalizable. So the examples that you might think of are like a rotation matrix, right? If you rotate by 30 degrees, then there's no eigenvectors. So it's not diagonalizable. Or you could have one eigenvalue so if your 2 by 2 matrix has one distinct eigenvalue, so you have a repeated root, right? Then the algebraic multiplicity is 2. And in order for A to be diagonalizable, the geometric multiplicity has to be 2. And the only way that can happen is if your matrix stretches the whole plane by that eigenvalue. So it would have to be a diagonal matrix. So let's just write down the possibilities. So for 2 by 2 matrices, right, either it's just, there are just no eigenvalue, no real eigenvalues, in which case your matrix isn't diagonalizable, or you could have one distinct eigenvalue, and then if you have one distinct eigenvalue, then this is diagonalizable only when A is a constant multiple of the identity. It's just, okay, let's say that the eigenvalue is, let's say that the eigenvalue is C. Then the only way your matrix can be diagonalizable is if it's just C's along the diagonal and everywhere else it's 0. Or you could have two distinct eigenvalues. Again, two distinct, all these are referring to real eigenvalues. And in this case, it has to be diagonalizable, because the algebraic multiplicities are 1, and that forces the geometric multiplicities to be 1, and then they're equal. Okay. So for 2 by 2 matrices, it's actually, I mean, the vast majority of the time, it's going to be diagonalizable. Okay. I mean, if it has any eigenvalues at all. Okay. Let's do a 3 by 3 example. And then we'll go back to finding the P and the D and the P inverse later. That, I mean, we basically already have done that. But for now, we're just focusing on the test for diagonalizability. So that's 2 by 2 matrices, and now let's do a 3 by 3 example. Yes, so next example. So let's say that you have this 3 by 3 matrix A, which is 5, 8, 16, 4, 1, 8, negative 4, negative 4, negative 11. Okay. And you're given that the characteristic polynomial of A is P of lambda is negative parentheses lambda minus 1 times lambda plus 3 in parentheses squared. And then the question is determine if A is diagonalizable. By the way, just as an aside, diagonalizability has nothing to do with invertibility. So you shouldn't you shouldn't think that they're in any way related. Okay. Because can you come up with a diagonalizable matrix that's not invertible? Yes, you could just have a diagonal matrix with a 0 on the diagonal. That wouldn't be invertible, but it's diagonalizable, right? And you can have matrices that are invertible, but not diagonalizable. Well, the identity matrix, wait, hold on, that is diagonalizable. How about the identity matrix where you have a 1? Do you remember? This is a common trick. You can take the 2 by 2 matrix, that's just the identity, but then in the first row, second column, you change the 0 to a 1. Right? That would not be diagonalizable, but it's invertible because the determinant is not 0. Okay, so anyway, determining if A is diagonalizable. Okay, let's see. And there are other things too. So one common question is, let's say you take a matrix and you row reduce it. Does that change the eigenvalues in general? Or the eigenvectors? And the answer is yes, right? If you take an invertible matrix, that invertible matrix could have lots of different eigenvalues, but then when you row reduce, you get the identity matrix, and the identity matrix, the only eigenvalue is 1. Right? So in general, the eigenvalues change when you do row reduction. So yeah. Okay. So anyway, going back to determining whether this matrix is diagonalizable. Okay. Well, you're given the characteristic polynomial. In theory, you could compute it because you just compute the determinant of A minus lambda I, but it's kind of a pain because it's not very easy or quick to compute this determinant. So you're just given the characteristic polynomial, and you're asked to determine whether A is diagonalizable. Well, first we should compute the eigenvalues. Well, that's easy. That's just the roots. So, okay. So the eigenvalues are 1 and -3, right? And first of all, we should just make sure that the characteristic polynomial splits. Does it split? Yes, right? It's fully factored. There are no quadratics that can't be factored in PMX. It's all just the product of linear factors. So it splits, that's fine. And so A could very well be diagonalizable. We just don't know yet. Okay. 2 distinct eigenvalues, and we want to find the geometric multiplicities and see whether they match the algebraic multiplicity. Well, there's one eigenvalue where we can immediately figure out what the geometric multiplicity is. So what is that? Right, it's this one. We know, because we know that the algebraic multiplicity, the multiplicity of the lambda minus 1 is 1. And so the geometric multiplicity, the dimension of the one eigenspace has to equal 1. So we know, without even having to really do anything, that the geometric multiplicity equals the algebraic multiplicity. Okay. The real question is the second eigenvalue, -3. We want to know the dimension of this eigenspace. So we need to figure out a minus lambda I. Well, what's that going to be? You have to be careful with the minus signs because it's a minus negative 3i, so a plus 3i, and that's going to equal, so we just have to worry about this. A plus 3i, so let's figure out what that is. You just add 3 to the diagonal entries. Okay. And of course, this matrix is invertible, right, as it should be. Sorry, it's not invertible as it should be, because we know that that negative 3 is an eigenvalue. This matrix has a null space. That's non-trivial. It's not invertible. But what we need is the dimension of this. We need the dimension of the 3 eigenspace. And remember, how is this dimension related to this matrix? Is it the rank? No, it's the nullity of this matrix. Right. So we need the dimension of the null space, and we know the fastest way to do it is to figure out the rank. Now, what's the rank of this matrix? Well, I see that these 3 rows are all linear combinations of each other. I mean, yeah, because like if you take the second row, right, this first row is just 2 times this first row. The first row is 2 times the second row, and the third row is negative 1 times the second row. I mean, they're all just multiples of the same row. And so what's the rank of this matrix? 1. Right. 1 linearly independent row, or 1 linearly independent column. And so what's the null space? Well, by rank nullity, it's 3 minus 1 is 2. And so what do we conclude? Is A diagonalizable? Yes, we conclude that A is diagonalizable. Right. So since the algebraic multiplicity equals the geometric multiplicity, for each eigenvalue, A is diagonalizable. Let's take a look at another example. So let's say you have this matrix A, which is 3, 3, 0, 0, 1, 3, 0, 0, 0, 4. So is this diagonalizable? Is A diagonalizable? All right. Well, we're not given the characteristic polynomial here. We have to compute it, but fortunately it's not very difficult. So the characteristic polynomial A minus lambda I is going to be 3 minus lambda, and then 3 minus lambda, here 4 minus lambda, 1, 0, 0, 0. And now what's the determinant of this guy? So P of lambda, so that's the determinant of this matrix, is, you could do cofactor expansion along the first row, and so you're just going to get, for the 3 minus lambda term, you're going to get 3 minus lambda times 3 minus lambda times 4 minus lambda. And if you do cofactor expansion along the first row, you have zeros, and so that's just not going to do anything. So this is the characteristic polynomial. And so the eigenvalues are lambda 1 is 3, lambda 2 is 4. Okay. And again, I see that the geometric multiplicity, so the algebraic multiplicity of lambda 2 is 1, so that tells me that the geometric multiplicity is also 1. And so the only work you have to do is for lambda 1, which is 3. So now we need a minus lambda I, so a minus 3i. And what are we trying to find again? We're trying to find the dimension of the 3 eigenspace and see whether it's 2 or 1. Those are the only possibilities. So a minus 3i gives me, oh, well, that's easy. It's just this. And so what's the rank of this? What's the rank of this matrix? 2. Right? Because I have 2 linearly independent rows, and then the top row is a linear combination of the second and third rows. So the rank is 2, and therefore the nullity is 1. Uh-oh, so what does that tell you? What should the nullity be if this matrix is diagonalizable? It should be 2, right? Because the multiplicity, the algebraic multiplicity of lambda 1 is 2. But we found that, so the geometric multiplicity is 1. The dimension of the 3 eigenspace is 1. And so no, A is not diagonalizable because the geometric multiplicity of 3 is less than the algebraic multiplicity of 3. Okay. So fairly straightforward, actually. It's just a matter of being careful once you get to, I guess the main things to be careful of are making sure that you remember that you want the nullity. Once you get to a minus lambda I, you have to find the nullity, and that's the dimension of the eigenspace, not the rank. Okay. So that's a bunch of examples of testing for diagonalizability. It's actually pretty straightforward though. But what about writing in the form A equals PDP inverse? I mean, we sort of have already done that, right? Your D is just the eigenvalue matrix, and your P's are just the columns are the corresponding eigenvectors. Well, let's just do a quick example. So let's say you have this matrix A, which is four, 1, 3, 6. So part A says find all eigenvalues of A. All right, well, let's do that. First, we need the characteristic polynomial. Well, characteristic polynomial of a 2 by 2 matrix is really easy because we have the formula. Right? It's just lambda squared minus the trace, the sum of the diagonal entries. So 4 plus 6 is 10, so minus 10 lambda, and then plus the determinant. That's 24 minus 3 is 21. Now we need to factor this. I think it's going to be lambda minus 3, lambda minus 7. So the eigenvalues are lambda is 3 and 7. Okay, that's easy. And so is this matrix diagonalizable? Yes, right? Because I have two distinct eigenvalues. In general, if you have an n by n matrix and you have n distinct eigenvalues, then your matrix is diagonalizable because the algebraic multiplicities are all 1, right? And so the geometric multiplicity also has to be 1, and so they're all equal. Should I just write that down? So in general, if A is an n by n matrix, and A has n distinct eigenvalues, then what's going to happen is your characteristic polynomial is going to be like some constant times lambda minus lambda 1 through lambda minus lambda n. And so the algebraic multiplicity of each eigenvalue is 1, and then that forces the geometric multiplicity of each eigenvalue to be 1. And that implies that your matrix is diagonalizable, right? The characteristic polynomial splits into a bunch of linear factors, and the algebraic multiplicity equals the geometric multiplicity. Okay, anyway, going back to the example, part B. So find P and D so that A is P, D, P inverse. Okay. Oop. And we have our matrix above, 4, 1, 3, 6. Well, D is easy. D is just going to have the eigenvalues, and now we just need the eigenvectors. So for lambda 1 equals 3. Okay, now I'm going to have to do some scrolling. Okay. A minus 3I is 1, 1, 3, 3. And so can you figure out an eigenvector of this matrix really quick? How about 1, negative 1? You just need, I have, this second row is just 3 times the first row, and so to produce a vector in the null space, you just need one vector that's orthogonal to 1, 1. Because my null space is one-dimensional. And similarly for 7, lambda 2 is 7, A minus 7I is minus 3, 1, 3, minus 1. I feel like we've done this example before. No, it's just a coincidence that you can use 1, negative 1 and, oh wait, no. Before it was 1, 1. This time I think we're gonna need, how about 1, 3? Yep, the dot product is 0. And so once we have that, it's just a matter of putting it together. So P can be 1, 1, 1, 3, and D is gonna be 3, 7. Okay. And one more question says, so find a simple expression for a to the m for any positive integer m. Well, okay, so this is leading up to this one application of diagonalizing matrices. So the point is that if you can write A as P times D times P inverse, let's think about what A squared would be. Well, that's just A times A. That's this matrix times this matrix. Right? Now what's interesting is that P inverse, I have a P inverse times P there. And that's the identity. Right? Times D times the identity times P times D times P inverse. And when you, oops, nope, there's no P there. And when you multiply a matrix by the identity, that doesn't change it, right? So this is going to be P times D times P inverse. Well, I have D times D is D squared. So A squared is P and D squared P inverse. Now think about what happens if you do A cubed, right? If you had A cubed, you have P D P inverse, P D P inverse, P D P inverse. And the P inverse P's, this one's going to cancel, and this P inverse P is also going to cancel. So you're going to get P times, and then I have 3 D's here. So it's going to be D cubed P inverse. So in general, a to the m, if you just do this like m times, this is going to equal p times d to the m times p inverse. And so that's just a general fact, right? So if A is P dP inverse, that forces A to the M to be P d to the M P inverse. And so going back to this particular example, with that particular A and D, the answer is just going to be A to the M is P times D to the M. Well, when you have a diagonal matrix times a diagonal matrix, the diagonal components just multiply by each other. So this is 3 to the M, that's 7 to the M, and then this is just the inverse, like this. So you can leave the answer like this without actually having to compute the inverse or multiply it all the way through. Okay. And so this is something, I don't think we have time to go over applications. I gave one application of eigenvalues and eigenvectors on the homework. And if you have a diagonalizable matrix, you can use this to examine the long-term behavior of certain processes. But we don't have time to talk about that. Maybe in a separate video that would be sort of optional. But the main things for the section is just knowing how to do the things above. Right? So in other words, how to tell if your matrix is diagonalizable, how to find P and D such that A is P dP inverse. And of course here, again, there's multiple different P's and D's you can use. Right? And so, is there one that we didn't do? We had one that, a 3x3, that was diagonalizable. Yeah, here we had A was diagonalizable. Now you can also find P dP inverse for this too. Right? Because you have eigenvalues. So let's see if we can quickly figure out what P and... We might not be able to do this quickly. But D would be easy, right? D would just be... So I have eigenvalue of 1. And then I have an eigenvalue of -3 with multiplicity 2. So that's going to be my diagonal matrix D, and then to find P, I would need eigenvectors. I would need a 1 eigenvector, and I would need 2 linearly independent eigenvectors with eigenvalue -3. But that will take a bit more work, right? You're just finding a basis for the null space of A minus lambda I. And then you just stick in those eigenvectors for P. I mean, it's the same process as for a 2x2 matrix. Okay, so that's all I think I want to say about diagonalization. And so hopefully we'll have time to do some review problems.